having just finished a inelastic collision with the same mass. Meaning that the next thing we needed to look at was what occurs when the heavier one is moving and the stationary one is lighter. Again, these are all going to be inelastic collisions. Plug this in. For gain's sake, what this is an air track. It's pumping up air from all these holes, creating a small layer of air between the part and the track, meaning that this is frictionless because there's no contact. There is a minimal amount of air resistance because the surface area is rather small and we're moving at low speeds, so air resistance is rather negligible. We can remove energy from the system due to heating of the rubber bands hitting the ends, but otherwise, all the energy stays in here. There is a slight tilt to this, so they will try to accelerate it that way. I didn't quite get it level. All right, questions on the setup? All right, so we had a stationary lighter one and a moving heavier one. Again, we're just looking for observations about what we're seeing after collision. Just for the sake of argument, it's acting more weight. And one more time. And what observations do we make about the collision?
Faster than half, but slower than the velocity that it started with.
Okay, so faster than half, but slower than original velocity. What else? Okay, so carts are more compact. Others. How about a comparison between the first trial with weights and the second two? Anything you noticed? Say again?
From the first one moving,
More weight you've got, less velocity you lose. Okay, that's accurate. More weight of the moving one. Less lost velocity. All right. So now let's change it up and take a look at it with the heavy one being stationary. So I'm just going to go here. Heavy one stationary. Again. Heavy one still stationary. And we're going to reduce the mass on this one. All right. So compared to when the heavier one was moving, what was different? Okay, slows down. But isn't that similar to what was happening when the heavier was moving? Okay. Less than half the speed. Okay. All right. How about comparing the two different mass setups? How
about?
A little bit faster when it's less mass and stationary.
Okay. Faster when stationary was less massive. All right, so we've just gone through inelastic and elastic collisions, talking about 6 different possible scenarios, all of which include one of the objects being stationary. Now, we could talk about them from situations in which they are both moving. This seems like it would be a much more complex system. So if I were to turn this back on, and let's say we're both moving towards each other, we could make some observations there, or we could talk about them both moving away, or this one moving slow, that one moving quicker, or we could swap this for an elastic collision. Just to swap out the right tools here. Again. Oop, too much. Now, I can come up with another easily 12 scenarios based on this, right? Why is it worth our time to just write those about these 6 ones when we're neglecting situations where both could be moving? Why do I not have us go through and write down all the observations for both moving scenarios? Say that again?
The final effect is the same as if you had one stationary and one with the other one moving with different velocity.
Okay. Elaborate?
Velocity is relative.
Velocity is relative. So yes, it has the same effects because velocity is relative. So we could look at this in terms of every one of these having different velocities and different combinations. Alternatively, we could always consider the frame of reference of one of the carts, and that means that no matter what our collision setup is, we can always consider one of them to be stationary by switching our frame of reference. By changing your frame of reference, you can simplify any collision down to these 6 scenarios. That means that for any mathematical approach that you've got to look at for momentum, you can then assess what that answer should be based off a conceptual understanding. By switching frame of reference so that you've got one being stationary, you should be able to predict what's going to happen with your mathematical answers before you've even plugged in any numbers, meaning that you should be able to check your answers conceptually anytime you're doing a momentum problem. Make sense? Questions on that? Okay. Then let's go ahead and actually take an approach to momentum mathematically. So, I'm actually going to pause this for, no, we're going to keep going for now. So, mathematical momentum. We'd already mentioned that momentum as a property that's conserved means that the sum of the momentum in one dimension must be equal to the sum of momentum in another dimension, or the same dimension after a collision. So if we have something like a pair of cars, and let's say this car has a mass of 1,000 kilograms, and it's traveling at a velocity of 5 meters per second, and its driver is on their phone because they're leaving the high school and driving up towards the circle, and they rear-end another vehicle that has a mass of, let's say, 800 kilograms, and is only moving forward at 3 meters per second. Now, in the scenario we're going to talk about, we are only going to talk about completely inelastic or completely elastic collisions. So for this scenario, we're going to say it's an inelastic collision. What does that mean occurs?
They keep moving together. How could that, give me some examples, how could that physically happen?
Kind of like the car and 45 meters per second kind of just keep pushing the other car forward.
Okay, so they ram into each other and they keep pushing each other forward. But when we talk about some of those ones where the heavier one was moving, the secondary one just winds up moving very quickly. So typically that just launched this first one forward. So give me a little bit more about how could this happen such that it's an inelastic collision.
There's a huge piece of Velcro on the front car.
Okay. Sure. Well, friction wouldn't matter in this case because the friction that occurs is between the tires and the road. That would mean that when they collide, they're doing something like this. Okay, so something causes them to lock together. Maybe the bumpers get hung up on each other. Maybe one car slams up on top of another because this guy's got a jacked up vehicle and this guy's driving, you know, El Camino, winds up in the bed. One way or another, an inelastic collision has the two vehicles stick together. What I would like you to do is try writing out an equation for what you think momentum conservation would look like based on your experience with energy conservation laws and the understanding that this is the mathematical version of momentum conservation. So give it a minute, see what you would write out. I'll get to you, Ed. Inelastic do not conserve. KE, because work is done. Ed, what's your question?
So, in every problem, will you tell us if it's elastic or inelastic?
9 out of 10 times, yeah. The 1 out of 10 times that I don't tell you, it's going to be pretty obvious, like pool balls clacking together. Pool balls don't stick together, right? So that's going to be elastic. Why are you putting Velcro on everything? Aside from assessing the kind of situation with cars, no, I'm going to have to tell you if they get hung up on each other or if they bounce off each other. Pool balls, pretty obvious, it's elastic. If I were to even give you something like a tackle in football, I have to tell you if he just shoulder checks the guy or if he grabs him and takes him to the ground. So it does have to be explicitly stated somehow. All right. Questions on this? All right, I'm going to change the situation a little bit. We're going to keep the same cars. We're going to keep the same traveling, but this time one car doesn't get hung up on the other. Now, if that's the case, then that means we're talking about an elastic collision. Elastic. And I'm going to write out the conservation equations here with you real quick. And they start out the same. Momentum 1 plus momentum 2 equals momentum 1 final plus momentum 2 final. Now notice I haven't grouped them together this time. Why have I not grouped them together? Right, they're not moving in the same with the same velocity. Okay, so that means that I could rewrite this as mass 1 velocity 1 plus mass 2 velocity 2 equals mass 1 velocity 1 final plus mass 2 velocity 2 final. And I could write this out in terms of energy. You'll notice with just this equation, I've got two unknowns. With just the information provided, I can't figure out how fast either of these is going to be traveling. Therefore, I have to rely on the fact that in elastic collision, kinetic energy is also conserved, so that I can say half m1 v1 squared plus half m2 v2 squared equals half m1 v1 final squared plus half m2 v2 final squared. Okay, let's just cancel out those halves. All right, so do I now have the ability to solve this equation? Is it mathematically possible to solve? Let me put it that way. Yes, I've got two unknowns, I've got two equations. Okay? What I'd like you to do is spend the next bit of class here seeing if you can solve this. And I'm going to give you a hint, and that has to do with the fact that we only took notes on 6 specific situations. Why did we only take notes on 6 specific situations? Because you can, you can change your reference frame. Why would changing my reference frame in this problem make life easier? Okay, so one of my velocities winds up at 0. Okay, what I'd like you to do, take some time, see if you can put together a way to solve for, I'd accept either one of these velocity finals. See if you can solve for either one.